You are watching an instructional video of the Miller Index activity developed by the Southwest Center for Microsystems Education. This activity is part of SCME's crystallography learning module that can be downloaded from the SCME website. The Miller Index is a roadmap or directional compass for identifying the crystal planes and directions in a crystal lattice. The objective of this video is to help you to determine Miller Index notation for crystal planes and vectors. In this tutorial, we will use the Cartesian coordinate system, or the XYZ coordinate system, to describe the crystal structure. Keep in mind that other systems are often used for more complex crystal systems. In the Miller Index notation, vectors are used to denote a direction within the crystal lattice. Square brackets are used to denote a primary vector, and carets denote a set of all vectors which are parallel to the primary vector. Crystal planes are denoted using parentheses for the primary plane and braces for the set of planes parallel to the primary plane. The graphic here shows a set of 1, 0, 0 planes, the 0, 1, 0 plane, and the 0, 0, 1 plane, all of which we will discuss in this video. Now for this activity, we'll be using 3 strips of foam core, which represent the 3 axes. You can also use rulers or rigid sticks. The tape is used to set up the X, Y, and Z coordinate system. String is used to show the vectors or directions, and a square or rectangular board is used to illustrate the planes. To begin this activity, an X, Y, and Z coordinate system is created using the 3 sticks. As shown here, the axes are at right angles to each other. Once built, each axis is identified as either X, Y, or Z. To better understand vectors and planes, imagine a cube with one corner at the origin and 3 edges along the X, Y, and Z axes. This cube can be thought of as a unit cell of a crystal. A crystal's unit cell is the simplest repeating unit in a crystal. A crystal forms when the unit cells join together, creating a lattice structure like the one seen here. Let's start with identifying vectors. The vector shown in this picture runs from the origin in a direction parallel to the x-axis. This is the 1, 0, 0 vector. 1 unit in the x direction, 0 units in the y direction, and 0 units in the z direction. Think of it as starting at the origin and taking 1 step in the x direction and 0 steps in the y and z directions. Let's look at another vector. This vector runs from the origin to 1 unit in the direction of z and no steps or units in the directions of x and y. Therefore, this is the 0, 0, 1 vector. How about this one? What vector is this? Well, if you take 0 steps in the x direction, 1 step in the y direction, and 0 steps in the z direction, then you will have the 0, 1, 0 vector. These pictures here show the 1, 1, 1 vector from both the side and top views. Imagine the 1, 1, 1 vector traveling through the unit cell. This vector begins at the origin and travels diagonally to the opposite corner of the unit cell. This point is denoted by moving 1 unit in the x direction, 1 unit in the y direction, and 1 unit in the z direction. Looking at both the side and top views, what is the vector shown here? Well, if you notice that the vector travels midway between the x and y axes, but does not travel in the z direction. Therefore, 1 step in the x direction, 1 step in the y direction, but 0 steps in the z direction gives you the 1, 1, 0 vector. What is this vector in yellow? If you said 1, 0, 1, you are correct. Identifying planes in a unit cell is very similar. Planes are denoted relative to the corresponding perpendicular vectors. For example, a 1, 0, 0 plane is perpendicular to the 1, 0, 0 vector, which also happens to be the plane that intersects the x-axis as shown. The 0, 1, 0 plane is perpendicular to the y-axis, and the 0, 0, 1 plane is perpendicular to the z-axis. Let's look at a demonstration. Here is the 1, 0, 0 plane. Notice that this plane is orthogonal to, or at a right angle to, the x-axis. Therefore, the 1, 0, 0 vector is orthogonal to the 1, 0, 0 plane. Thus, the x notation is 1. Notice that the z and y axes do not intersect the plane. Therefore, y and z are denoted as 0 and 0 respectively. The family of planes parallel to this 1, 0, 0 plane would also be denoted as 1, 0, 0, but with braces. This plane is parallel to and does not intersect with either the x or z axes. However, it does intersect the y-axis at a right angle. Therefore, it is denoted as the 0, 1, 0 plane. Note that all the planes parallel to this plane are also denoted as 0, 1, 0. Can you name this plane? If you said 0, 0, 1, then you are correct. Since the plane is perpendicular to the z-axis and the 0, 0, 1 vectors, but not to the x and y. Also, the tabletop is parallel to this plane, and it is also denoted as 0, 0, 1. This one is a bit more tricky. Can you tell me what plane this is? Well, notice that the 1, 1, 0 vector is perpendicular to the plane and that the plane does not intersect the z-axis at any point. Therefore, if you said 1, 1, 0, then you are correct. Now how about this one? All three axes, the x, y, and z, intersect this plane, and the 1, 1, 1 vector intersects the plane at a right angle, or is perpendicular to this plane. So if you said 1, 1, 1, then you are correct. For more in-depth information and practice on Miller Index notation, you can complete the Miller Index activity in the SCME Crystallography Learning module. Download this module from the SCME website under Educational Materials.